Welcome you all to the term paper presentation on network topology based influential spreader identification. Myself Giridhar Maji, and this work is done under the guidance of Dr. Somo Sen, Assistant Professor, A.K. Chaudhary School of Information Technology, University of Calcutta. So there are many problems that are nowadays modeled as network, where there are nodes that represent some kind of entities and the edges or links between them that denote the interrelationship or interconnection between the nodes. For example, in case of online social network, the profiles or the persons are the nodes, and the relationship between two persons, the relationship is the link or the edges. Similarly, there are road network, power grid network, airline routes, co-authorship network, citation network. For example, in airline network, the airports may be the nodes, and if there is a route from one airport to another, then there is a link or edge. So in this way, many kind of problems could be modeled as a connected graph or network. Now, when we model some problem into as a network, then many interesting events could be explained using such kind of network modeling. For example, rumor spreading or misinformation spreading, or we can say viral marketing, etc. Now, when we model as a network some problem, then we have access to a lot of very efficient data analytics tools that are already developed for different graph modeling, graph theoretical purposes. So we can use them uh, efficiently if we can model any problem into a network model. So what we aim to do in this paper presentation, we would like to tell that there are certain problems that are modeled in as a network, and we like to find out the which nodes or which users are the most influential one, the important one or the central one. For this purpose, in graph theory there are certain already existing tools or metrics. Those are known as centrality metrics. Let us see them now. There are three very basic centrality metrics that are very simple, like degree centrality. In case of a network or graph, degree centrality is the number of incident edges on a vertex. That is the degree, how many other nodes are directly connected to that node. So if a concerned node is connected to many number of nodes, then we say its degree centrality is more. So it is measured as by the number of its node degree. And if the assumption is that if a node is connected to many other nodes, then its centrality value is more. Similarly, another is proposed, which is known as betweenness centrality, and this measures that how many, if we are considering for a node, suppose we are considering the betweenness centrality for a node V, then we need to know that in the network how many paths from any other node pair moving through V. So suppose there are some node S and another node T, that is start and source and target, and that the path from S to T, there are multiple paths between S and T, and a certain number of paths are going through the node V. Then how many number of paths are going through V divided by total number of paths between S and T gives us the betweenness centrality. So if many number of paths are going through V, then V is very much central. So another example could be given, like if there are two cities or two part of the city, and in between there is a river and only one bridge is there. Now this bridge is connecting the first part of the left part of the city to the right part of the city. Then if we consider it as a network or graph, then any point in the left side, any node, and if is connected to the node in the right side through the bridge. That is, if we consider two end of the bridge as two nodes, then all the path from left part to the right part going through that two nodes that are the bridge. So in this case, the betweenness centrality value of those two nodes is very high. That is, they are very much important node in that assumption. Similarly, another is closeness centrality, where the average closeness of a node to all other nodes in the network is calculated. Much closer it is to the concerned node is very close to all other nodes, then its measure or the closeness centrality is high, it ranks high in the list, so it is very central. So this is the as it is the in the opposite, like if centrality is value is very low, that means it will be ranked very high. So its measure is 1 upon average 1 upon summation of the distance, that is average distance between all nodes. Now what you see that this degree centrality a local measure, like in this case degree is uh, computed locally, and other two, closeness and betweenness, are computed over the complete network, so they are more time consuming. Now let's come to another kind of centrality later proposed from the K-core decomposition technique of network pruning, that is called KSL decomposition. So in this is kind of different from the other already discussed three methods. In this case, what is done? Suppose this is, we are considering it as a toy network with 16 nodes and it has 21 edges. Now this what this KSL decomposition is do, it first removes the let me first clear it that this technique will assign a KSL index value to all the nodes. That is the measure of it, and depending on the based on the this measured value, that is KSL index value, the nodes will be ranked, that which node is very high or most important, and in this way. And it will, the nodes will be categorized into different cells, or you can say different basket or bucket or set. So the set of node which has the very highest KSL index value, that will be called as core cell. Now let's say in the very first how this algorithm works, it first starts with all the node that has degree 1, that is the nodes that are connected with only a single link. So we see that this node V14, V15, 16, 13, 12, these are connected to only with one link, that is they are all degree 1 node. In the first step, we remove all those degree 1 nodes and assign them KSL value of 1. They are assigned to the KSL in the KSL with KSL index value of 1, that is called the outermost cell. Now as soon as we remove these nodes, we see that now V11 has become degree 1 because these three nodes are removed. So again, if we see that some more node getting degree reduced to 1, then we also assign them to KSL index 1. So V11 is also added to this list, KS is equal to 1 list. Now we see that there are no more nodes. These 4, 5, 6 nodes are removed and there are no more 1 degree nodes. Now we increase the value of KS to KS is equal to 2. So now we are looking for KSL index 2 value nodes. So that is second case, second cell nodes. Now we see that V10 has degree 2, V9 has degree 2, and V8 has degree 3. Now we first remove V10 and V9 now and assign them to KSL2. Now we see that once we remove these two and V11, V8 has only degree 1. So as this is less than 2, we are considering KSL is equal to 2. So any node, if after pruning becomes of less degree than that, like for this case degree 2, then it should also be removed and added to KS is equal to 2. So V8 is also added. Now we see V7 has only 2 degree. So V7 is removed and added. Now once V7 is removed, V6 has only 2 degree, so V6 is also removed and added. V5 become 1 degree, so V5 is also added. Now we see that there are no more nodes that is having degree 2 or less. So this is KS index 2 is done. Now we increase KS is equal to 3, and now we see that V1, V2, V4 all are having 3 degree 3. So all those are going to the KS is equal to 3. Now all nodes are done, processed. So the nodes are divided into three cells. Ks is equal to 1 outer cell, Ks is equal to 2 middle cell, and Ks is equal to 3 the innermost or core cell. So as per this KSL decomposition, this nodes V1, V2, V3 and V4, these are the most central. Now this has certain drawbacks of this cell, that we see that KSL places a lot number of nodes into each cell, but actually we want to get the most important, but we are getting here 4 nodes in the first cell. So KSL is not able to distinguish between these 4, and this effect is known as rich club phenomena, where these 4 nodes are connected very closely to each other, but there may be some node which is not inside this closely connected layer, but that may be very important in respect to the topology of the network, but KSL is not able to identify such kind of nodes. So then in 2013, Cheng and Zhang, what they did, they improved upon the KSL. And how did they do that? What we see already, that in every step KSL is removing some nodes, and removed nodes have no contribution in the later process. But what they did, the authors started that removed nodes should also have some importance in the further steps. So they divided the degree of the of a node into two parts. One part is the degree from the removed nodes. They called it as exhausted degree, and another part is degree from the remaining nodes, the remaining connections, remaining number of links, that is residual degree, and they combine them using a lambda, that is a free parameter lambda, tunable parameter, and computed mixed degree value. That is km, this mixed degree value is the residual degree of the node plus lambda into the exhausted degree. Now they started decomposing the network similar in a similar fashion of the KSL, but instead of using the degree, they now started to use the mixed degree value. And for example, here I have shown the stepwise. In the very first step, there is no nodes are removed. So in this case, the exhausted degree is 0 and mixed degree value will be the residual degree. That is all. In this case, very first step, all have their normal degree values as the residual degree. Now first 1 degree nodes are removed. As 1 degree nodes are removed, now in the second step, when we are considering this V11 in the second step, now the mixed degree value will change for this. This is the difference from the KSL value, because now if we the authors have taken lambda value of 0.7. Let us consider the same value and compute V value for V11. What will be the mixed degree value of V11? It will be, it's we need to know its residual degree. Residual degree is, it is connected to the rest of the network, that is one link, so residual degree is 1. And what will be its exhausted degree? It is connected to 3 extra removed nodes. So there are 1 2 3 removed nodes, so it's there will be 3 ke, that is exhausted degree will be 3. So its mixed degree value will be 1 plus 0.7 into 3, that is 2.1 plus 1, that is 3.1. In such way, for all the nodes we compute the mixed degree value, and then the similar way we decompose it, and in this case we will get more number of cells instead of only 3 cells. So the ranking will be more monotonous. Now, so what we see, we have seen that we have seen two kind of centrality measures or node ranking measures to find the influential nodes. One is that we using the degree or Never's degree kind of thing, that is the local measures that consider only very local limited information, and another is closeness, betweenness, or KSL. These are the global measures. Now global measures has local measure is very quick to compute, and local measure takes very global measure takes very large time, because it has to consider the all the complete network, and complete network information is processed, then only we can have the metrics like betweenness or closeness. So it is very much time consuming, and for a very large scale network it is sometimes not feasible also. So in recently many kind of hybrid measures are proposed, where the authors have combined the benefits of local measures and global measures, like they have used degree as well as some closeness or betweenness, but to a little extent, only maybe up to 2 hop 3 hop. So let's, in the next slide we'll see some of the recent hybrid methods that are proposed to overcome the limitations of both the global and local measures and the get the balance the benefit. Now, the first one is the improved method by Liu et al. In 2013. They proposed this improved method theta to improve upon the KSL. What the problem we faced in the KSL? It places a large number of nodes into a single cell. So what Liu et al. Tries to do, they try to rank the node within the KSL. If a KSL something, suppose KSL highest core cell has 10 nodes. Now Liu et al. Try all the 10 node have same value, KS value is equal to the maximum KS value. Now Liu et al. Tries to rank them. These 10 nodes will be now ranked 1 to 3 kind of things. So distinctly ranked. So for that purpose, what they have done, they have considered that distance from the core cell of a concerned node, they assume that if this distance is less, they are connected to the core cell node, very strongly connected to the core cell nodes, then that node is very much influential. So in their formulation, this Ks max is the highest KSL value, that is the core cell nodes KSL index, and this is Ks is the concerned node. This V5 has the KSL value of Ks. This Ks is the concerned node is V, for which we are considering or computing the measure, and this Ks max is the maximum core cell. If we consider our toy network, this Ks max is 3, and if you are suppose considering Ks is equal to 1, this V will be the very outer edge nodes, outer layer nodes. For this Ks will be 1, and this duv is the distance of this V or concerned node from any other nodes of the core cell. This U is the core cell node. So U is the core cell node. Like this KSL max, we have seen V1, V2, V3, V4. There are 4 core cell nodes, and suppose we are interested in computing V15, then this Ks will be 1, Ks max will be 3, and this distance will be the distance of node V15 to V1 plus V2 plus V3 plus V4, because those 4 are the core cell nodes. In this way, this improved method computes the measure. For all node, it computes this measure and then rank them based on this measure. Now coming to neighborhood coordinates method by Bay and Kim in 2014. In this case, this is kind of simpler, that what they did, we also know that KSL values are also known as coordinates values, because the core cell, we call it the innermost cell as the core cell, so coordinates. So this what this neighborhood coordinates does, it computes or aggregates the coordinates values of its neighborhood. Suppose V is the concerned node, so we first compute what are the nodes, what nodes are there in its neighborhood, and then we add up the KSL values of all the nodes in its neighborhood. Suppose this V has 3 neighbor, then V1, V2, V3, then we first compute the KSL value of V1, then V2 and V3, and add them up to get the measure, neighborhood coordinates measure. So we compute this for all the nodes, then rank them based on this value. So this is neighborhood coordinates. So the basic assumption, underlying assumption by B and Kim is that if a node's neighbors are having very high coordinates value, then it also becomes important. So if any node has neighbors, those who are very influential in terms of KSL value, then the neighbor is the concerned node is also influential. Now in 2016, Mayatol proposed gravity formula. In this case, what they have done, they have computed, suppose the measure as following the gravity formula. For a suppose for a node V, we want to compute the its using gravity formula. Then this KSL KSV is the KSL value, KSL index of V, and this KSU is one of the neighbors of G. Any node, it can be any node from the first level of neighborhood, or from the second level of neighborhood, or from the third level of neighborhood. Then the U is a distant node, and KSU is the KSL index value of U, and this D is the distance between the concerned node and the U node. Now this U belongs to psi V. This psi V is the set of nodes depending on the how many layer, how many hop we want to consider. If we only want to consider the only nearest neighbors, then this D will be always 1 and U will belong to only the next neighborhood. So if we want to psi v may contain two hop neighborhood, then the first neighbor, second neighbor. So in this way we can consider up to multiple neighborhood, and these authors have proposed up to 3. They have computed the perform experiments considering three layer of neighborhood or 3 hop neighborhood. So distance become 1, 2 and 3. Now neighbors degree. This is proposed by Pei et al. In 2014. Here what they have done, this is similar to this neighborhood coordinates. Here they have computed, aggregated over the neighbors degree. So their assumption is that if degree is high, then that node is important, and if the all if a no, all the neighbors of a node are important in terms of degree, then that node is also important. So they have computed, aggregated the sum of the degree values of a node's neighbors and assigned them as their neighbors degree measure, and based on that measure they have computed, ranked the nodes. Now, in gravity method, Liu et al. In 2019, this is a very recent work. In this work, what they have done, they have in this work they have considered the similar gravity formula that is done in Ma et al. In 2016, but instead of using the KSL index, they used the degree. So degree of the node and degree of the neighbors node or any distance node and the distance. Now what another improvement they have done, one improvement is that instead of KSL they have used degree. So degree is less time consuming to compute, easily available, so it takes less time. Another thing they have done, instead of the authors have assumed that up to 3 level of neighborhood, but in this gravity model the author have selected up to d by 2, that is d is the network diameter, so up to d by 2 level of neighborhood considered. So they have provided some network parameter based formulation. Instead of arbitrary saying that 2 level or 3 level, they have used the network diameter. So half of d by 2, if network diameter is d, so they have considered up to d by 2 level of neighborhood while computing this their measure, and based on this measure they have ranked the nodes. So these are some of the recent methods, and now let us consider if we apply all these methods on our network, the toy network shown earlier, so how the nodes are ranked. So in our network, this already we have mentioned that there are 16 nodes and 21 edges, and we have applied different methods on our toy network. Now, based on the degree, the degree value, we see that the first rank will be the node 4. Then in the second rank, we have node 11, node 8. These are the V4, V11, V8, and only we see that based on the degree we get only 1, 2, 3, 4 ranks. Now depending on the KSL, already we have seen that we get 3 cells. In the innermost cell KSL index 3, we get 1, 2, 3, 4 nodes. In this case we get this middle layer and the rest of the nodes in the last layer. Now this is mixed degree decomposition. We see here 1, 2, 3, 4, 5. We get five different ranks. Similarly, this is weighted KSL. This is neighborhood coordinates, neighborhood coordinates plus. This is improved method. Here we see that 1, 2, 3, 4, 5, 6, 7, 8, 8. Similarly, this is local centrality. This is gravity. Gravity gives 1, 2, 3, 4, 5, 6, 7, 8, 9. Total nine different ranks. So what we observe from here, this computation of the on the toy network, that most of the hybrid ranking technique performs better, that use as this use multiple centrality metrics in their formulation, they perform better in general than the individually degree KSL or MDD, as they use both kind of the benefits of from the local centrality as well as the global centrality. Now as a conclusion, what we see that there are many methods that are applied to applied to the network models or graph models for the purpose of identifying the most important nodes or most important persons, and this such kind of problem can be used in viral marketing scenario, or information spreading, rumor spreading kind of scenario. And this but these node ranking techniques are not one fits all type. Like same technique may not be applicable to all kind of networks. Depending on the type of the network or the network parameters, the topological parameters, the completeness of the network, the performance differs. So one method can be good for one kind of network, but that may not be similarly effective or similar performance can be achieved in other kind of networks. So also there are we have seen that for MDD there is a parameter lambda. Similarly, in many other techniques, heuristic technique considers different kind of free parameter, tunable parameter, and these tunable parameters are very tough to tune for different networks, because the what optimal getting the optimal value, the best value requires many trial and error. So there are problems. So there is no global or universal ranking method that could be applied blindly to any network. So there is always a research area, active research is done in this area in the search of a good ranking algorithm that is efficient in terms of computational complexity, and as well as in terms of matching the accurate influence, or accurately mapping the nodes based on their influencing power. Also, there is another problem that we could not discuss in these slides, but the problem remains. That is, many existing studies overlook the problem of spreading overlap. So a spreading overlap is something when some information reaches to a person from multiple sources, and each of the source can consider him as an influenced person by him. Then this kind of scenario is this called as spreading influence overlap. Actually, it should be considered once. If I have received some information from person A, then later person B and person C also gave me the same information, but only the credit should go to person A, the very first person who has given me the information. But many existing studies consider influence A, B, C all as the influencer. So this kind of problem is also there in the existing studies, and depending on the limitations and merits and demerits of the existing studies, there are many scope of work on this area, on this domain, like already discussed. And there are another this that the whatever we have discussed until now, these are on the modeled networks are undirected, unweighted. But in real life, most of the cases, model networks are at least weighted. For example, in case of road network, so if as per unweighted model, the all roads are having same weight, but that is not the case. If there is a highway, 8-lane highway, and there is a normal village road, both links between A and B, the both links, both wages could not have been same weight. If we model as real world problem, the highway should have much more weight than a simple village road or one-way road. So in real life, most of the networks are weighted, and there are certain situations where the network must be directed, because something propagates from one way to another but not in the reverse direction. So in those kind of scenario, we have to consider directed networks. So in both cases, how these algorithms work in that kind of networks, or we may need to improve or to port them or modify them to be used in the weighted and directed network. So that is an ample scope of work. Again, another kind of network, in case of especially in case of online social network, that we whatever network we are considering are static networks, so they doesn't change, the topology or the interconnection does not change with time. But in case of social networking, that never happens. Whatever network we are considering, there is a snapshot at a time, sometime. But after some time, or after a day, I may have new connections to new people, new friends, or I have removed someone from my friendship, I have exchanged something, some information. So the nodes, the topology, the link, the weights, all changes with time. There is evolving dynamic network. So in such kind of network, if we like to compute who is the influential user, then does existing techniques for static network work there, or we need to improve upon them, or in that case we need to run multiple times the algorithms, how we can incrementally, because not the whole network changes, only part of the network changes, topology changes. So can we do something that the existing algorithm will be used, but not every time we should not compute the exhaustively, but only we have to arrange something that only the incremental part is computed every time. So such kind of problems are there, which could be many opportunity, provide many opportunity for research. So thank you. And these are the references, some of the references used in this presentation. Thank you.